Hello, my name is Isabella and I will be your host today for another mathematics video brought to you by RJ. For the video, I ask you, when is an image an integer? And no, I'm not talking about a picture of a number. First, let us define a few terms. Image, definition, an output that a function produces. Likewise, a pre-image is an input of a function. Integer, definition, any number that can be produced by the number 1 under addition and subtraction. 1 is an integer. 1 plus 1 equals 2. 2 is an integer. 2 plus 1 equals 3. 3 is an integer, and so on. It can go in the opposite direction as well. 1 minus 1 equals 0. 0 minus 1 equals negative 1. Negative 1 minus 1 equals negative 2. Negative 2 is an integer, and so on. Fractions in between, called rationals, are not integers, such as 1/2, 2/3, 3/4, 2/5, 4/5, and so on. Numbers in between those, called irrationals, are also not integers, such as phi, e, pi. Let us work with the most basic function, the identity function. F of x equals x. The outputs are the same as the inputs, or the images are the same as the pre-images. Now I'm going to graph the function. I have bolded the points where the images are integers. All of the other points are not integers. There's an issue here. Sure, we can see when the image is an integer, but the function itself does not tell us when the image actually is an integer, which is what we want. We will now adopt a convention. Since images can only be numbers, our convention will be 1 means yes and 0 means no. Perfect for binary. This means we want a function that produces a 1 whenever the image is an integer and 0 if not. Is this possible? Let's look at the decimal part function. The images of this function are the decimal part of whatever is inside the curly braces. The decimal part of 1 equals 0. The decimal part of 2.125 equals 0.125. The decimal part of 3.14159 equals 0.14159. Now let's look at the floor function. The images of this function are the integer part of whatever is inside the floor bars. The integer part of 1 equals 1. The integer part of 2.125 equals 2. The integer part of 3.14159 equals 3. But we don't want to know what the integer is, just if it is an integer. Since the decimal part function goes from 0 to 1, excluding 1, if we place the decimal part function inside the floor function, that might help us. Uh-oh, we have a problem here. This should equal 1 because 1 is an integer. How can we fix this? The decimal part of any number can never equal 1. Furthermore, it equals 0 whenever the pre-image is an integer. Therefore, if we subtract it from 1, we end up with a function where the images are 1 when the pre-image is an integer and less than 1 otherwise. If we place this inside the floor function, we obtain exactly what we want. This is suitably called the integer test function. The closed form of the decimal part function is if we substitute this into the integer test function, we get, this doesn't look too pretty with the inverse tan and cotan. So we can construct the integer test function another way that doesn't look so complicated. We know there's a pattern in the integers. They occur every 1 unit. Therefore, we can use an oscillating function. The general form of an oscillating function is B is the period, or how often certain numbers occur. I just said integers occur every 1 unit, so B equals 1. A is the half height. By our convention, our images are 0 and 1. The distance between 0 and 1 is 1. Half of that is 1/2, so A equals 1/2. D is the vertical shift. Oscillating functions are centered at 0 by default, which means they range from -a to a. We need to raise the function by 1/2 for the images to be 0 and 1, so D equals 1/2. And since A also equals 1/2, I'm going to factor the 1/2 out. C is the horizontal shift. Since cosine of 0 is always 1 and 0 is an integer, there is no need to shift it. Therefore, C equals 0. Now, we just place this inside the floor function as everything less than 1 will drop to 0. And we have a nicer version of the integer test function. Let me graph this. As we can see, the function is 1 whenever the image is an integer, and 0 when it is not an integer. So yes, it is possible to have a function that tells whether or not images are integers. We just constructed 2 equivalent functions that do so, called the integer test function. Remember, we use the identity function at the beginning. So for any function, the integer test function is I hope you enjoyed the video. Thank you for watching.